Hi and welcome to the speech. We will hear about high throughput DNA sequencing. Magnus will tell us about the basics. He will give us a short view in the history and in the future. And we will hear about chances, risks, and challenges of this new technology. Please welcome Magnus. He has programmed Wikipedia and works as a bioinformatician. I hate this word, I think. Okay.
Test 1, 2, okay. I realize it's a talk after dinner, or lunch for some. So if you fall asleep, try not to snore too loud, as you might wake your neighbor. I'll tell you a little about DNA sequencing and the rather remarkable progress this field made in the last year. And this is where I work and where most of this happens at the moment. It's in the UK, where we're all under tight surveillance, and I'll have some about this later. Okay, little basics. As you might remember, all life forms have DNA, and my laser pointer is not working. Oh, there it is. They all have DNA regardless of the level of complexity. And you can go down from chromosomes and disentangle them and end up with a well-known double-stranded helix, which has 4 bases that are abbreviated with A, C, G, and T. Hence the title of my talk, All Your Base. And the genome size does not correspond with organism size or organism complexity. So we go from 3,500 bases with some bacteriophage, which is a virus that infects bacteria, all the way up to human with 3 billion. But then we find some single-celled organism with 670 billion bases. So sequencing is a challenge even with some apparently simple organisms. How did it all start? Started in the 1970s by a team, I think, in France. They sequenced the aforementioned bacteriophage, 3,600 bases, which took the entire team, I think, 5 or 6 years. And they were using this phage because it has RNA instead of DNA, which is related, but for technical reasons much more simple to sequence. Then people started developing DNA sequencing methods, and one of these was a wandering spot method, which yielded 24 bases per experiment, which involved quite a few people working on it. And then finally, in '75, Frederick Sanger, who actually got not 1 but 2 Nobel Prizes in his life, he invented a method called chain termination sequencing, which quickly became the most used method because it actually yields some tangible results. So you have your strand of DNA. Here it's a single strand. They have to be separated for this. And then you have a so-called primer. The primer is a small DNA sequence, 20 or 30 bases. Okay, I hope this works better. And this primer has to match your DNA you want to sequence. And from there, you extend one base, then you look what base it was. Then you extend another base and another and another. And you have to record this somehow. And in the beginning, it was done with radioactive atoms that were incorporated in the bases that were added, which, having worked with radioactive gels, I can tell you it's a pain. Everything's slightly radioactive after the experiment, so you have to wait like 2-3 days for everything to cool down before you can continue to work. But then they replaced the radioactive parts with fluorescent dyes. And this is basically what most of the sequencing that was done till last year, or beginning of this year actually, and this is still done like this. Looks like you get these 4 overlaid curves in 4 different colors, and the peaks all mean it's one more base there. And this looks all pretty, but soon these peaks will start to degrade, and they will all bleed into each other, and then you have to stop with this sequencing because you can't tell the bases apart anymore. In practice, you get something between 300 and 1,000 bases per run, as we say, per experiment, and we need a primer to start with. And most of you will remember the Human Genome Project from the news in 2001, when the President of the US and the Prime Minister of the UK announced that the human genome is now sequenced, which it wasn't, and it still isn't. And they started in 1990, or they started earlier, but they began the actual work in 1990. Was exactly this process. And they started at one end of a chromosome, or at least a fragment of a chromosome. And then they was this primer here in red, and then they sequenced some more. So now they know the sequence of this fragment. And then they take the end of this fragment and use it as a primer to start the next part, and so on. Now, human has 3 billion bases, and you can sequence roughly 500 to 600 per experiment. Now, this has several drawbacks. Not yet. Sorry. Because first, you have to wait for this run to complete before you can even think about starting this run, because you don't know this yet. And then you have to wait for this to complete before you can start the next part. The other thing is that you actually need scientists to do this, because you can't just take the end of this and run it. You have to actually look at this whole sequence, and sometimes you have to start a little more early, because bases are not, they don't have the right GC content and blah, blah. So this required all highly trained personnel. And then in came this guy, Craig Venter, who took a little more a business approach to this. Quite literally, he tried to beat the Human Genome Project with the sequencing and then patent all the genes. Which luckily didn't work out. Otherwise, it would all be a patent violation. And he said, well, I don't actually want to do this in a row like this, and then this, and then this. I just start somewhere, and I have my entire genome, and I just start somewhere and get 600 bases. And then I do this again, and again, and again. And if I do this often enough, I get the entire genome just by pure chance, and I get these fragments overlapping, and then I use a really big computer to puzzle them all together again. This means, first, there's little need for scientific supervision, so you can have some guy who basically reloads the machine, presses a button, and it produces another of these fragments, and then that gets stored, and then you do this again and again. And this scales up rather nicely, because you add more machines, you add more people who operate the machines, and you just scale up. This doesn't, the old method doesn't scale up, because it has to wait for each step. And this was done, so parts of the human genome were, even by the Human Genome Project, were assembled, were sequenced this way. And you might think, oh, that's great and all, and there's now this new technology, originally called Solexa. This was then bought by a company called Illumina, who basically bought everything in this segment of the market. Again, with a chain termination method, you get rather long reads compared to earlier methods, a few hundred bases in a stretch, but it's still few. So it takes a while it takes a machine a while to run one of these fragments, and you can scale it up, but it's still kind of slow. And Solexa takes this method that Craig Venter thought of, so-called shotgun sequencing, because like a shotgun, you don't have to aim that carefully, just aim in the general direction of the target and pull the trigger, and things will work out fine from there. So Solexa said, well, maybe we don't have to do these long sequences. We do shorter ones, like 30 bases, 40 bases. But we do lots of them. And with lots of them, I'm not kidding. So what they do is they take DNA raw material, and they fragment it to a certain size. So let's say 200, 300, 400 bases. So they just chop it apart in some nebulization processes. I don't even know what they do exactly, but this is what they end up with. So this is the original DNA fragmented to fragments of roughly the same size. And then they attach these fragments to glass chips. So millions and millions of these fragments now stick to glass chip. And then they use a method called PCR to amplify this. So each single fragment becomes a cluster of thousands and thousands of copies of this special fragment. And then they sequence these things all in parallel, and with each base, for each base, they stop and take photographs of this. And this is really photographs. It's a high-resolution digital camera. And this is what it looks like. It's not the screen from Poltergeist, and it's not something from the Hubble telescope. This is what the Solexa sequencing looks like. So it produces lots and lots and lots of these images, which then have to be analyzed. To the right, you see the Solexa machine. So each of these is one machine. And in here is a so-called flow cell, which is this thing here. It's rather tiny. It's like my laser pointer. And photographs are taken from this. So this is a very, very tiny portion of this flow cell. And if you do